So the first excited state from the particle in a box is a great place to start talking about what we might call quantum interference. Because if we look at the probability distribution for that, so we got the x-axis here, the probability distribution on the y-axis, we have this two-lumped camel. And the question about the probability distribution, this is a particle in a box. Where's the particle, right? That tells us the probability of finding the particle on anywhere in the box is equal to this function with two maxima. It's nice and symmetrical, but where actually is the particle from the point of view of a particle? Is it over here on sort of the left-hand side of the box, or is it over there on sort of the right-hand side of the box? And it's a bizarre thing. It's sort of confusing because in the end, the answer really is both. And in this little video, we're going to begin to explore the implications of that. The idea is that quantum objects really can be in multiple places at once because they really are waves, and waves by definition have some extent. So all this is really saying is that there's an extent to them, but it gets a little stranger than that. And it's a variant of what we're going to see a few times in the term that really bothered Einstein, and he called it a thing called a spooky action at a distance. Or also, if you've heard about quantum entanglement, really fundamentally this simple particle in a box in an excited state is a simple example of that thing called quantum entanglement. In fact, so far we've treated photons really as if they were particles, and we call them photons, and I've shown you that there's ample evidence for that, but that's a little bit backwards. And what we're going to do is go way back to a thing called the two-slit experiment. It's a real classic experiment from classical physics. And in fact, I'm posting as well a link to a video from MIT that goes through and shows you an example of the two-slit experiment using a laser, where you'll see it actually occur. And there's also some interesting discussions and even a nice little model, toy that you can make to actually give yourself a two-slit interferometer, if it's called, if you want to go about that. So the idea here is that we've got some sort of screen with a little opening and then another little opening. And those two openings there at the bottom are what we're going to call the two slits. And there's some light heading toward, or any really wave-like object. You can think of it as an ocean wave heading toward a jetty, heading toward that object. But what we're going to do is we're going to block off one of those slits with this red barricade here, so that we're only going to, this wave, this light or this ocean wave or anything is only going to propagate through that one hole. And from the hole, the wave propagates away in circles from that point source. And you can do this in a bathtub, or you may have seen it at the ocean. And then at some distance away, we're going to place a target, some film, the seashore, anything you want that, a microchannel plate to actually count photons and electrons as they arrive at the surface of the slit. It really doesn't matter. So we're going to count the objects there. And now the wave's going to continue to propagate. And so once it hits that slit, we have these green circles that I'm drawing. And notice that they're pretty evenly spaced to the extent I can do it with my fine artistic skills here. And what those green lines are, those are what we call the peaks of the wave. So the wave has got peaks and troughs, and it's propagating like this. And so all those green circles is heading off in that direction. All those green lines are just the high points of this wave, right? So those red circles show you those high points as it propagates away. But the wave is moving. It's a wave. It's wavy. And so a little bit later, it'll have progressed forward, and it will look more like this. It'll have come 90 degrees forward, and so then the white bits are where the wave is high, and the green bits are in the trough of the wave, where the amplitude is at a minimum value. So if we look at the average intensity, the average height of the waves at the shore, or the average intensity of the light, we're going to find that it's brightest right in front of the slit and sort of diminishes away in a very smooth pattern as we go away from the slit like that. So there'll be nothing very interesting. At any given point, the wave will be going up and down over time, but the average intensity will be just this very, very smooth pattern like that, or think of it literally as the average height of the waves as you're moving along the seashore is another good example. So that's the average intensity. Now I need some of the space here, so let's see, using the magic of this video, we got to kind of erase some of this stuff here. Let's get rid of that average intensity because we don't want it anymore. Those waves, I need that space, so we'll get rid of that wave propagating over there, but we're going to leave the green wave fronts. And most importantly now I'm going to remove that barricade. So we're going to get rid of that barricade. And now we're going to let another set of wave fronts propagate through there. We're going to draw them in purple just so we can tell them apart. So there's another set of wave fronts, the same wavelength. They're coherent, meaning that the waves are hitting those two slits. It's a nice parallel coherent wave on the outside. And I need a few more of those green waves. And now let's look at this, because these wave peaks of this, from the green slit over on the right and the purple slit over on the left, are interacting with each other. Remember, those lines represent the peaks of the waves, while the white spaces are the troughs of the waves, but they're both propagating. So they're both oscillating up and down in time in there. And so where we find these waves, the peaks crossing each other here, the green and the purple curves are intersecting. I've circled in red. At those points, if we look at any given point in time, the green wave is going to look like that, and the purple wave is going to look like that, and they're perfectly overlapping. The peaks are lined up with each other. That's why we have the red circles. And so those waves are going to add together. And the overall intensity of the wave is going to be like this red curve. It's going to be essentially twice the amplitude of either one or the other. And we call that constructive interference. So the two waves are working together and they're building up intensity together. Now on the other hand, let's look where we have a peak in the purple wave, but a white bit, a minimum, a trough in the green wave. And so there we have a situation where the waves are not overlapping each other. One is high and the other is low. The peaks and the troughs are overlapping. So here's a green wave here. Here's a purple wave here. And you see that the green trough matches a purple peak. And then there's a green peak and a purple trough, and et cetera, et cetera, et cetera. So they're perfectly what we call out of phase. And then when we add them together, we get nothing. We get a flat line. So that is called destructive interference. And the important thing is that the location of those points of constructive and destructive interference, that doesn't change. So you get this standing pattern of constructive points and destructive points in this harbor behind this jetty with two holes. And you can see that if there's strong ocean waves hitting a harbor, or more to the point, we get the standing intensity of light coming through these slits and hitting our film or our detector or whatever. So now let's get rid of a little more stuff because I need some more space. And we can draw now the average intensity hitting that beach or that photographic plate or the detector. And where the red points are, we're going to get high average intensity. And where the blue X's are, we're going to get low average intensity. And that pattern is completely different from the pattern that we saw beforehand when we only had one slit open, when we blocked one of the holes in that jetty there. And so this interference pattern is the absolutely gold standard for recognizing that something is a wave. When you can make waves interfere with each other, that's not something that particles can do. It's only something that waves do, and consequently, it's an identifying characteristic of those waves. The way the two-slit works, the two-slit experiment works, is a wave is an extended object. And as long as the wave that's coming up to those two slits, or one slit, has the same wave length and the same what we call phase, the peaks are in a nice line on the outside of the slit, then the important bit is that the wave is going through the one or two slits at exactly the same time in exactly the same phase. So it has to be an extended object like that. So now let's take the two-slit experiment and remember the fact that we've already established that photons are individual objects. And so we can turn down the intensity of our source, which is typically a laser, way, 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 way down. We can turn it down so low that we have to use those photomultipliers we were talking about to detect the light. Or we can use some other devices, microchannel plates and things that allow us to figure out where the light was at the same time. So here's our simple schematic for the experiment. We've got our two slits and we're ready to go. The two slits are going to be some distance apart. I drew 500 nanometers here. They can actually be a millimeter apart, half a millimeter. It changes the pattern, but it doesn't change the idea very much. And we're going to have such faint light that we're going to see the photons arriving, bip, 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 one at a time, like a Geiger counter, very much like a Geiger counter. In fact, what a Geiger counter is doing is counting photons, gamma photons, very high energy photons from nuclear decay. And so we're going to get them one single photon at a time. So the first thing we'll do is block off that first slit again. And remember that we expect the average intensity to look like that. But we have to build up the pattern. We got to collect photons one at a time. Bappity, 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 bap. So they come on in. And every one has a unique position when it hits that plate. But eventually, we'll build up what we call the statistics and find that most of the photons, in fact, hit just across from that slit, and the intensity, which is the number of photons per unit distance on our detector here, goes off with a nice smooth pattern as we move away from that area of the maximum amplitude there. Now let's do a little racing again. So we get them one at a time, all right? So let's get rid of that. Let's get rid of our photon counting. And most importantly, let's get rid of that block. Let's get rid of that second slit. And now from the two-slit experiment, remember we expect an intensity like this if we're dealing with waves, right? So if the waves go through both slits at the same time, then they're going to interfere with each other, and we're going to get this pattern built up like this. But we're sending the photons in one photon at a time, right? So they're coming in, the photons are coming in from the bottom of the screen here, and it's like a ski racer at the top of a ski slope. They're being sent down one at a time. One photon's coming along. And yet when I build up the statistics of this, the intensity winds up looking like that. I haven't built them all the way here because I ran out of patience making my little dots. But you see what we'll find is that in fact the photons will exclusively show up where we have the maxima in the two-slit intensity pattern, and you'll get essentially no photons in these low points where the probability distribution, which is the intensity, is at a minimum. So again, this is one photon at a time, and we still get the same interference pattern. That is really, really weird because it absolutely demonstrates that each and every photon saw that slit and that slit. Saw the purple slit on the left and the green slit on the right. Each individual photon, which we identify as a corpuscular object, as a single thing, went through in a real way, in a fundamental way, it went through both slits. You cannot describe it as having gone through one slit or the other because that interference pattern is conclusive proof that you had a wave that encountered the two slits. You only get the interference if you go through two slits. If you cover one slit up, you get that smooth pattern, and in fact that's what you see. And only when it goes through two slits do you see that. So that is a fundamental demonstration of this wave-particle duality business. It really does happen that way. And you want to know something even weirder? So a buddy of mine, a guy named David Keith, who got his PhD in physics at MIT, working for a fellow named David Pritchard, he actually, for his PhD project, he set up an interferometer, which is what we call this two-slit thing, using nanofabricated gratings, and actually sent individual, I think it was sodium atoms, through these slits, and you see exactly the same thing. You have to make really, really narrow slits because the de Broglie wavelength of the sodium atoms is extremely small, but he did that. It was in the dawn of nanofabrication. And if you send individual sodium atoms, which once again you count one at a time using a detector, through a very narrowly spaced slits, you see exactly the same thing. So not only are photons being waves and interfering with themselves as they go through the two slits, but being single objects that you can count one at a time, but sodium atoms will do the same thing. Facing two slits, a single sodium atom is going to arrive on a detector beyond those two slits with a probability distribution, with an intensity pattern that is consistent only with that individual sodium atom having sampled, if you will, gone through is another way to put it, both slits. You cover one up, and the pattern changes completely to that uniform intensity distribution. So this de Broglie relationship of wavelength, momentum, but values of individual identity for individual particles, this wave-particle duality, absolutely holds. And it holds for photons, it holds for sodium atoms, which will count as protons in our three heroes, and it holds for electrons as well. If you send them through a similar interference pattern, they're going to behave the same way. So all three of our three heroes have this critical, crucial property that they behave like waves and they behave like individual objects. And you can prove it using this two-slit experiment.